Okay, thank you. Thank you for coming, everybody. It's really nice to be here. Uh, yeah, I will be talking about gravity waves today, which are not gravitational waves. Gravity waves are fluid oscillations that propagate inside of stars or planets or many other environments. This is a really nice simulation of the sun, and so you see convection in the outer layers of the sun, but that excites gravity waves that propagate in the interior of the sun. And there's an enormous amount of physics that you can learn from gravity waves. So my goal of this talk is to convince you that gravity waves have all the exciting astrophysics, whereas gravitational waves are just this trivial outcome of general relativity that was solved a long time ago. So for those of you who came all the way from Princeton expecting to hear about gravitational waves, sorry to disappoint you, but I do have a little bit of a fix for you. One thing I've been working on, which I won't focus on in this talk, is white dwarf binaries that in-spiral due to gravitational waves. We're starting to find a lot of those with ZTF at Caltech, including this system, which is the shortest orbital period eclipsing binary star known. It's two white dwarfs that orbit each other just under 7 minutes. This is a really nice find by Kevin Burge at Caltech. We've already measured the orbital decay due to gravitational waves of this system with enormous precision. So it's a really beautiful system, and we have many others in the pipeline. We have a 20-minute that was just published. We have a 14-minute, a 24-minute, a 40-minute. So we're finding a lot of these, and we're going to be able to start constraining the population of emerging white dwarfs. So that's a really exciting thing that we're doing with ZTF in addition to transients. Another thing I won't talk about today, but I've worked on, is the spins of black holes. So, of course, we're starting to measure spins of black holes with LIGO, spins of merging black holes. And what the data is showing is that most black holes here have chi-Fs is what's actually measured, have spins that look like they're pretty small. And this is somewhat of a surprise for many people, but I've been doing a lot of work on angular momentum transport in stars. And the basic predictions of those models is that most black holes should be born rotating very slowly due to the fact that most of the angular momentum gets removed from the core as the star evolves and actually gets lost and never falls into the black hole. So there are some binary evolution scenarios like these points up here that do lead to rapid rotation, but for single black holes at least, they should be born slowly rotating, and many binaries will be slowly rotating as well. So gravity waves are really useful for seismology in many different contexts. Last time I was here, I talked about how you can measure magnetic fields inside of stars using gravity waves. We can also detect them even in Saturn. We can detect gravity modes of Saturn. I'll talk about that at lunch, I think, so I'll skip over it for right now. And for this talk, I'll focus on some of the effects of gravity waves. In which astrophysical scenarios do they actually make an impact? So this is a nice simulation of gravity waves by Andrea Cristini. This is a simulation of carbon shell burning in a massive star, maybe a few years before it collapses. And what you see is very vigorous convection here, where the burning is happening. But this excites gravity waves on either side of this convective zone. So what gravity waves really are, they should be called buoyancy waves. They are a wave that propagates inside of a medium where there's a buoyancy force. So if you take a fluid element and you push it downwards, the buoyancy force will push it back up, and you'll get an oscillation, and that's what a gravity wave is. So they tend to be pretty low frequency waves, but those low frequency waves are often excited by things like tidal forces or convection, which are pretty slow motions inside of stars or planets. So they carry information. You can do astroseismology with them. I also want to emphasize they're really common in astrophysics. They even exist in things like galaxy clusters. They can help heat galaxy clusters. They can do all kinds of interesting things. In this talk, I'll focus on some of their impacts, the energy and angular momentum that they carry and how that can impact a few different systems. So I'm going to start with the sort of small scale, low energy, move up to larger scale, higher energy systems as I progress. So I'm going to start by talking about the effects of gravity waves in tidal interactions. And I'll start with tidal interactions in giant planet systems like Saturn or Jupiter. So in these systems, you typically have a big planet surrounded by several very tiny moons. And those moons in these systems, just like our own moon, they migrate outwards away from the planet because the planet is rotating much faster than the moon's orbit. So the moons extract a little angular momentum. due to tidal dissipation inside of the planet. They migrate outwards. Then the moons themselves can get caught in resonances with each other, and you can get all kinds of tidal heating of the moon. It's a very rich dynamical problem. But one piece of the problem we don't understand very well is the dissipation inside of the planet that's driving the migration of the moons. So I've worked on this a bit recently, and I think there's some modifications to the classical picture of tides that people usually think about, which is you normally think about, say, the gravity of the moon excites a tidal bulge on the planet. If that tidal bulge were perfectly aligned with the moon, you'd get no torque, but because there are dissipative processes inside of the planet, the bulge is misaligned with the moon at some angle, which is basically 1 over this tidal quality factor, Q. That's how people like to parameterize tidal dissipation. And that's the classical picture, and if you know Q, you can calculate the torque, but actually calculating Q is very difficult. So I'd like to emphasize that in most cases in astrophysics, we think that tidal dissipation is probably actually due to dynamical tides. So dynamical tides are not this classic picture of a tidal bulge excited in the moon or planet or star, but rather some kind of wave that's excited inside of the planet. So it could be gravity waves, and that's one thing I've worked on. It could also be inertial waves. This is something Jeremy's worked on a lot. This is a plot of energy dissipation due to tidal excitation of inertial waves in a giant planet with a core. And what you see, you get a similar feature from gravity waves. You see that at most frequencies, the dissipation rates are fairly small, but there are certain discrete frequencies where you get much larger energy dissipation rates. And so if you had a moon located forcing the planet at one of these frequencies, then you get a lot of tidal dissipation, you get rapid migration. But you can say, oh, probably the moon will not be at one of those resonances, and so the dissipation will be slow. But turns out that's maybe not a good way of thinking about the problem. But I want to emphasize that instead of thinking about a tidal quality factor, it might be better to think about a tidal migration timescale, which basically just goes as the inverse of your energy dissipation rate. And this tidal migration timescale is just the time it takes a moon to migrate outwards. That's directly related to the energy dissipation rate. If you know that, you can calculate an effective tidal quality factor, but it's not actually that angle that I showed in that plot. So this is a calculation of a tidal migration timescale in a sort of toy model of the Saturn system, where at most semi-major axes, so these would correspond to different forcing frequencies of Saturn, you don't get very much dissipation, and the tidal migration timescale is quite long. But there are certain discrete locations corresponding to resonances with gravity modes inside of Saturn. And you could get similar features due to dissipation from inertial waves. So there are certain places where a moon would be resonant and could migrate outwards on very short timescales. So these resonances are narrow, but if you zoom in at the resonance and think about how the system will actually evolve, you realize that even though the resonances are narrow, they can be very important. And the reason is, if we put a moon out here away from a resonance, it will migrate extremely slowly. But the resonant locations themselves, they actually move. They're not static. That's because the structure of Saturn is changing over time. Saturn's contracting. There's things like helium rain going on. And so all these resonant frequencies are going to change. Their location will change. So if some of these resonant frequencies sweep outwards, then what will happen is the moon will get caught in the resonance. And you can think about that like this. Imagine this resonant location is moving outwards on some time scale set by the evolution of the planet. There's a stable fixed point near the resonance where the moon will migrate outwards at the exact same rate that this resonance location will migrate out. And it's a stable point because so if the moon's right here, it will move out at the same rate. If I perturb the moon outwards, it will migrate a little bit slower, and this resonance location will catch back up with the moon. If I perturb the moon inwards, it will migrate a little bit faster, and it will catch back up to this resonance location. So you can have moons get caught in these resonances, and that's what I like to call resonance locking. So even though the resonances are narrow, you might expect the moons to have gotten swept up by them and to migrate outwards with those locations over time. So you can think of the moons as finding one of these waves and surfing it outwards. So it's not a perfect analogy, but it's a nice way to visualize how the evolution of the system could proceed. So the point is that if this process is happening, you don't really even need to do a full calculation of, the dissipation produced by gravity waves or inertial waves. All you have to know is the rate at which those resonant locations are moving. And in this problem, as long as any of them have a frequency that's decreasing in the inertial frame or increasing in the rotating frame, that means that the resonant location is moving outwards and the moons can get pushed outwards, which is what we need to happen. So if you know the time scale on which that resonant location is changing, you can just calculate the migration rate of the moon. So I'm not going to walk through all this math, but you can just calculate it. And then you can talk about an effective tidal Q, but the point is really what's driving this whole process is the evolution timescale of the planet. So we can actually test this theory, which is one of the nice aspects of it. So I wrote about this a few years ago in a paper, and in some more recent work, I've been working with Valerie Linné, who does astrometric measurements of the locations of the moons. So he can actually measure their migration rates outwards. And we can talk about the effective tidal quality factor of Saturn that's measured, that's driving this outwards migration of the moons. So these are his measurements. The purple bars are the measurements. So what he's finding is for the 4 inner moons, the effective tidal quality factor is of order a few thousand, although it looks like there's some dispersion between moons. If you look at Rhea, which is the outermost small inner satellite of Saturn, the effective tidal quality factor is about an order of magnitude smaller. So this is, I think, already proof that some kind of dynamical tides must be at work, because in the equilibrium tidal theory, all these moons should have the same Q. So we already see Rhea has a very small Q. And the exciting thing that's happened recently is we've been able to measure the migration rate not just of these moons, these inner moons, but also Titan, which is much further away from Saturn. It's the biggest moon. And because it's so far away from Saturn, most people historically thought it shouldn't be migrating much at all. But Valerie has managed to measure that migration rate with astrometry. We've also been working with Paolo Tottora's group in Italy on measuring the migration rate of Saturn using migration rate of Titan using radio tracking from the Cassini satellite, which did some flybys of Titan. So it can measure Titan's position really accurately and measure this migration rate. So what that data is telling us is that the effective tidal quality factor governing Titan's outward migration is extremely small. It's of order 100. So this is, a couple orders of magnitude smaller than people had expected from equilibrium tidal theories. And it means that Titan is migrating outwards a lot faster than people had predicted. And we have 2 measurements that both give consistent answers, so I think it's pretty compelling data. So
the theoretical results here require a detailed model then, or interior structure of Saturn.
Yeah, so the theoretical predictions are these blue lines, and they don't actually, so in order to calculate these robustly, you need a detailed model of Saturn's internal structural evolution. What I did was just parameterize that in terms of a planetary evolution timescale. So you say that all these resonant locations are basically moving according to some timescale of Saturn's evolution, which we expect to be of order Saturn's age or a few times longer. And then I just leave that as a parameter and sort of move it up and down, and that gives me these blue points for Titan and Rhea. For the inner moons, it's a little more complex because they are in mean motion resonances, and so you can have these outer, Tethys and Rhea can just get pushed outwards by Mimas and Enceladus on their own. So you could have, in principle, no dissipation due to those moons.
Can you tell us a bit about the internal structure of Saturn? Some conjectures near the surface, where is the state of Saturn?
Yeah, so Saturn is convective in its outer envelope. It's still, simple models of giant planets don't have any stably stratified region, but one of the things I'll talk about at lunch is from Saturn ring seismology. It's pretty clear that there are gravity modes inside of Saturn that actually resonate with the rings. So there has to be a stably stratified region there. And so that can support gravity modes that can be tidally excited by moons. But I think, I was about to mention that I think it's more likely that inertial waves are actually the main player here. And part of the reason for that is that the prediction from inertial waves is that the migration timescale of all the moons should be roughly the same. It should be roughly the evolution timescale of the planet, whereas for gravity modes, you actually expect the outer moons to migrate a little bit faster. But when we compare the data, so if we talk about the migration timescale of all the moons, what the data is showing is that they're all migrating outwards on a timescale of roughly 10 years within a factor of 2 or so. And this is the basic prediction of migration due to inertial waves whose frequencies are changing as Saturn evolves. So it's, it's exciting that it looks like all the moons are, at least to first order, fitting this basic prediction of resonance locking. And it has some really important implications for the evolution of the system. Usually when people talk about Titan, they assume it hasn't migrated much. What the data is showing is that it looks like the outward migration timescale, at least right now, is of order a few times the age of Saturn. So if you track that backwards in time, you can predict approximately how far each moon has migrated. Now, it's a little dangerous to extrapolate this to the beginning of the solar system because this constant could change a bit. But it implies that most of the moons have migrated a substantial distance away from Saturn. And Titan may have formed much closer to Saturn. So that's an exciting result. We're still trying to understand all the implications. It also might help explain tidal heating of Enceladus. So Enceladus is heated at a pretty large rate due to resonance with Dione. And that implies a migration rate that's so fast, if you talk about the standard equilibrium tide formalism, then the measurements imply that Enceladus had to have formed just a few gigayears ago, and even worse for Mimas and Tethys. Whereas in the resonance locking theory, the effective tidal Q is actually changing with time, so that's what these colors are showing. And so it predicts actually slower migration in the past than you would have predicted otherwise. And that allows the moons to have been born closer to the formation time of Saturn, although even this model is predicting that Dione, Tethys, Enceladus, and Mimas may have actually formed well after Saturn. So they might have been spawned out of a giant ring system. I think that's still unclear, but we have a better picture of the long-term evolution of the system. Yeah, Daniel.
Why is it that the higher Qs seem to have a larger slope on this graph? Doesn't that mean faster evolution?
So yes, but remember that the actual migration rate, it depends very sensitively on semi-major axis. So Titan, in order to migrate out on a timescale of 10 gigayears, Titan has to have a really small Q because it's so far away from Saturn, whereas the inner moons can have larger Qs and still migrate out at the same rate.
So can you actually unbind a moon this way?
So I don't think you can unbind it. Eventually, the resonance locking is going to break. You can't have a moon migrate out arbitrarily far because you can't, in order to do that, you'd have to have sort of an infinite energy dissipation rate at one of these resonances. And so things like nonlinear effects are going to saturate the resonances. So it's unclear exactly how far you can move a moon outwards or how far out of a moon this could work for. But the data appears to show that it's working for Titan. So there's lots of implications. This could happen in exoplanet systems or many other systems. So another place where I think we see this resonance locking process happen is in heartbeat stars. So we're going to move up now from planets to stars. Heartbeat stars are a place where you can directly see gravity modes inside of stars. So what heartbeat stars are, they're just eccentric binary systems, typically orbital periods of days to weeks, very high eccentricity. And what you see in many heartbeat stars is you see gravity mode oscillations in the photometry. So typically these are discovered with Kepler. You see stellar pulsations, which are gravity modes that are excited by tidal forces. This is an example of one such heartbeat star, where the stars pass very close to each other at periastron, and that's what excites these gravity modes. You also get a change in the light curve at periastron due to just the fact that the star actually becomes visibly tidally distorted. But throughout the rest of the orbit, the tidal forces are weak, but if you excite a gravity mode, it just keeps on oscillating. Its damping time is long compared to the orbit, so it just keeps on oscillating. And then this process repeats.
Is that related to the frequencies being low, like you said?
Yes, so the typical frequencies we see in these heartbeat star systems are periods of one cycle, or frequencies of 1 or 2 cycles per day is pretty typical. And that's pretty low frequency as far as the star is concerned, whose dynamical frequency is higher than that. So these gravity modes in stars can be resonantly excited. And we see that in many cases. So here's a nice example of a different heartbeat star system, where you see the gravity mode here, and you see the tidal distortion at periastron here. And so each heartbeat star has a different fingerprint in terms of its light curve. Every heartbeat star looks different. You have all kinds of shapes depending on the eccentricity and viewing angle and the stellar components. Sometimes you see tidally excited gravity modes like here, sometimes you don't. So there's a lot of physics here. You can tell that these gravity modes are tidally excited because their frequencies are exact integer multiples of the orbital frequency. So essentially, these are modes who are not oscillating at their natural frequencies. They are driven modes. They're forced modes. And the forcing in an eccentric binary system can be decomposed into integer multiples of the orbital frequency. And so that means the gravity modes oscillate at exact integer multiples of the orbital frequency. The closer to resonance at which they're driven, the higher the amplitude they have. If you take a Fourier transform, you see many different peaks at integer multiples of the orbital frequency. So this comb of peaks here, this is mostly due to this equilibrium tidal distortion at periastron. But you see the dynamical tide right here. This is this resonantly excited gravity mode that you see in the light curve here. So like I said, some of these stars show gravity modes, some don't. Only like about a quarter of them actually show pretty obvious tidally excited pulsations. One of the most spectacular systems is this one, KIC 8164262. This is what I showed in that movie earlier. This is a system with an orbital period of about 90 days and a very large amplitude tidally excited oscillation. By the way, large amplitude here means 1 part per thousand. So pretty tough to see from the ground, but from space it's pretty easy. And in this case, you can't see it on here, but this is a gravity mode that oscillates exactly 229 times for every orbital period. So its frequency is exactly 229 times the orbital frequency. If you zoom in, you see this is the distortion right at periastron here, but most of the orbit we just have this gravity mode oscillating at roughly a few cycles per day. So this system is a good case for resonance locking because we see this really large amplitude gravity mode. It has to be driven quite close to resonance in order to get it to that amplitude. If you take a power spectrum of this system, it's dominated by that gravity mode. If you pre-whiten that, you get a bunch of other peaks due to other gravity modes. But this one is 30 times larger in amplitude. So that's unexpected to have one mode that's so much larger than all the other modes. But if you really want to understand what to expect in these systems, you have to do more work. You have to characterize the systems. So I led a program at Caltech where we got follow-up spectra of a few dozen heartbeat stars. These are the radial velocities for this star. It's a little noisy because it's rotating fairly fast. But we were able to measure eccentricities from this RV follow-up for many systems. Once you have that, you can characterize the system by modeling its light curve and radial velocities. So for this system, Kelly Hambleton did a really nice job measuring all the orbital parameters and parameters of the two stars. So in this case, it's a F-type star, temperature of about 7,000 degrees. So that's quite hot as far as Josh is concerned, but quite typical for these heartbeat stars with gravity modes. And a low mass companion, eccentricity of about 0.9 in this case. So if you want to predict the observed amplitude of these gravity modes, basically they're just sine waves. And their frequencies, like I said, are some integer multiple n of the orbital frequency. And their amplitude can be calculated. So there are many terms to calculate here. There's basically a tidal amplitude, a viewing angle effect, how well the mode couples with the forcing, a spatial overlap integral, and then a luminosity amplitude of each mode. The point of this is we can calculate most of these things once we constrain the system parameters. What's hard to calculate accurately is this resonant detuning parameter. So if a mode alpha is driven at its resonant frequency, so this is the forcing frequency, tidal forcing frequency omega n. If these frequencies are the same, this whole factor in the denominator becomes very small, and so you get a resonantly excited mode. Now, statistically, it's very unlikely to have a close resonance. But if you do have a close resonance, you'll get a very large amplitude mode. So what you can do for a system like this is once you measure the system parameters, you can calculate the number of modes that you expect to see above some amplitude A. So the blue line in this curve is the expected number of oscillations above some amplitude A as a function, so this is the number of modes as a function of that amplitude. So you have many low amplitude modes and very few high amplitude modes. And in this system, we see this very large amplitude mode with a luminosity fluctuation of about 10 to the minus 3, whereas we only expect that in less than 10% of systems like this. So it's unlikely to see a mode like this in this kind of star, but it's exactly what you should expect if a resonance locking process is going on. So in this case, what's happening is the orbit is circularizing, so the semi-major axis is decreasing. So as long as you have some mode that's increasing its frequency in time, basically that will allow the frequency of the mode to stay resonant as the orbit decays and the tidal forcing frequencies go up. So in this case, the stable fixed point would be at this location in this diagram. So the point is that we understand stellar structure quite well. We can calculate how fast their gravity mode frequencies are increasing in time. And that means you can predict the amplitude of a resonantly excited mode. You basically know exactly how much energy you need to dissipate in order to keep the mode at resonance. So that means you can predict the luminosity amplitude of the mode. And that's what's shown in this plot. So there's a lot to unpack here. The point is we see this very large amplitude oscillation at a few cycles per day with a very large amplitude up here, which is in this blue region of the plot. The background shading is basically the relative probability of seeing a tidally excited gravity mode in any part of this diagram. And it's very unlikely to find a mode up here because you need a finely tuned resonance. But it's exactly the amplitude you'd expect based on resonance locking, which are these green circles. So I think that's, again, a good indication that resonance locking can explain why we see this one dominant mode in the system, whereas all these other low amplitude modes are just near resonances, but not so finely tuned. So, and statistically, this distribution of predicted and observed modes matches. Now, of course, to get an exact match is basically impossible, but statistically, they match. Yeah.
Generally, as stars age, they expand and the density increases, the G-mode frequencies go down.
That's what you would think. That's actually, yeah, so it's actually not the case. They do expand, of course, but the inside of the star contracts. And so the Brunt-Väisälä frequency on the inside of the star is actually going up. So the many G modes, their frequencies actually increase with time. The coupling here is, yeah, there's some coupling. There's also some coupling at the outer part of the star. So the mode frequencies, some of them do decrease, but most of them actually increase with time. And in red giants, the G mode frequencies have increased to the extent that the core G modes are now the same frequency as the envelope P modes. That's another way of thinking about it. So there are many gravity modes that could be resonantly locked in these systems. That's the point here. So I'm doing some follow-up work with a student, Shelley Chang, a really great undergrad who's been modeling more of these heartbeat stars. We'd like to understand how common this is because we don't see this phenomenon in all the systems. So she's been modeling several more heartbeat stars, looking at their tidally excited oscillations, and seeing if those can be explained by resonances or just chance forcing that doesn't require any kind of resonance locking. So we have at least one system that's another good candidate for resonance locking, but it's also clear that many stars are not currently in a resonance lock. So we still need to understand how common resonance locking actually is in these systems. But it does appear to be at play at least in some systems. So next I'm going to move on to massive stars. Are there any more questions about gravity modes, tides, moon systems? Yeah.
Your equation showed a gamma term denominator.
Yeah.
Is this a ring down time?
I went through it a little fast. Yeah, so this is the damping frequency of the mode, the damping rate. That's right. So these modes have some dissipation. If they're not tidally excited, they'll ring down over time. But usually the damping rate is quite small. So it's much longer. The damping time is much longer than an orbital period. So the modes don't really decrease over one orbit. And usually this factor is much smaller than this factor. So exactly. Yep. Laurentian. Yeah, Dan.
So does the fact that you don't find many mean that stars just aren't evolving enough to find one?
So that's what we want to understand. In this case, for instance, there's a mode that appears to be consistent with resonance locking right here. But in this system, it's not evolving as fast. And also this star probably has a slightly thicker convective envelope, which means the mode amplitude, the photometric amplitude of the mode is smaller because it's more deeply buried inside of the star. So in this system, the mode that might be resonantly locked only has an amplitude of like 2 times 10 to the minus 5. So it doesn't jump out at you if you look at one of these light curves. But it could still be a resonantly locked mode. So we'd like to understand the distribution of what these amplitudes should be. They're higher and hotter stars. In cooler stars, which are more common, the convective envelope is thicker, so the gravity modes produce a smaller photometric signal. So we don't really know how common it is. Great question. I have a backup slide. Certainly probably a lot of them are triples. If you look at short period eccentric binaries, there's been some nice work by Raghavan or Tokavinen, I forget who did this, that shows that most of them are in triples or higher order systems. We actually have a lot of heartbeat stars that I think are in quadruples. And you can tell that, well, ask me about it at the end. I'll show you a slide that shows that. Okay. So for the last part of the talk, I'm going to focus on the effects of gravity waves on stars, and they can be really profound in massive stars. And in particular, I think they might be really important for driving pre-supernova outbursts. So there's been a lot of work over the last several years showing that many types of supernovae appear to come from stars that had some kind of violent outbursts in the final years or decades or weeks of their lives. One of the best known examples is supernova 2009 IP. This is a type 2N supernova. Here's the supernova event here. It didn't actually explode until 2012. There's still some debate about whether or not it exploded at all in this case. But it's called 2009 IP because we saw these eruptions in 2009. And then the star returned to quiescence, and then more eruptions in 2011, then it finally exploded in 2012. So people like to compare these eruptions to LBV outbursts. But LBV outbursts aren't that common. And there's evidence from many other types of supernovae. So type 1b, type 2b, type 2n, type 2p. Basically, there's evidence for many different types of supernovae that there's some kinds of outbursts in some of the stars in the final years of their lives. In this case, we see them directly. In most cases, it's inferred from modeling the supernova light curves and spectra. So when people try to infer mass loss rates from those observations, they can be, a tenth of a solar mass per year, or 1 solar mass per year, very large mass loss rates that are orders of magnitude larger than the quiescent mass loss rates of massive stars. So there appears to be something going on right before a star dies, not all the time, but in many stars, that causes them to lose mass at greatly enhanced rates. So one of the ideas proposed was originally proposed by Elliott Quadaert several years ago, that gravity waves excited in the core of the star can propagate to the outer layers of the star and help drive these outbursts. So to understand that, let's take a look at this movie which I showed you before. Again, this is carbon shell burning, and it excites gravity waves. The convection excites gravity waves, which will then propagate out towards the surface of the star. It can also excite gravity waves that propagate into the core and change its spin and things like that. But I'm going to focus on gravity waves that propagate up. Now this simulation only covered some box inside of the star, so it didn't actually see the surface of the star. But these waves can carry a lot of energy upwards. So the typical luminosities of waves, so how much energy you're putting into waves per unit time, scales roughly as the Mach number of the convection times the luminosity carried by the convection. And this Mach number in stars is usually quite small. Typically in the sun, it's like 10 to the minus 3 or so. So you only put a small fraction of that convective luminosity into waves. But the key insight with massive stars is that at the end of their lifetime, their cores start losing most of their energy, not by photons diffusing outwards, but by neutrinos. And what this means is that the nuclear burning has to proceed very rapidly in order to provide any thermal pressure support. So you get a situation where the nuclear time scale of the star can become much shorter than the thermal time scale of the outer layers of the star. So what that means is that the nuclear burning luminosity in the core of the star can be orders of magnitude larger than the surface luminosity. So all this energy generated by nuclear burning in the core, it either goes out by neutrinos, or it's trying to diffuse out very slowly by convection or by radiative transport, so you never see that energy at the surface. But some of that power of convection goes into waves. And the waves propagate through the star on roughly a stellar dynamical timescale. So they can actually carry energy from the core to the surface of the star before it explodes. So waves actually become the dominant source of energy transport in the final year or so of a star's life. So the typical scales we're talking about here are quite extreme. So neon and oxygen burning are a good example. Those happen of order 1 year before the star dies, depending on mass. But the convective luminosities in the core of the star during those stages can be something like 10 to the 10 L sun. That's 10 to the 5 larger than the typical surface luminosity. And that means we can put something like 10 to the 8 solar luminosities of power into gravity waves. So that's something like 1,000 times larger than the Eddington luminosities of these stars. So if those waves can propagate to the surface of the star, they can totally change what the star looks like, and they'll be able to drive an outburst because the fluxes can be so large. So the toy picture here is you have some very vigorous burning in the core. That excites gravity waves. But typically, in order to get to the outer layers of the star, the gravity waves need to couple with acoustic waves. So typically, they need to tunnel through some evanescent region in the star. Often that's due to a convective helium-burning shell that gets in the way. You can think of this as like an insulating blanket separating the core from the envelope. So we need to calculate what fraction of these waves actually tunnels through into acoustic waves that then propagate out to the surface of the star. So to do this, you need to understand propagation of waves in stars. This is what's called a propagation diagram of, in this case, I think it's like a Wolf-Rayet star but actually I think it's during outbursts. So what happens is we have our oxygen burning core here that excites waves whose frequency is something like a few times 10 to the minus 3 radians per second. Those propagate as gravity waves in the core of the star here, where that frequency is much smaller than the star's Brunt-Väisälä frequency or its Lamb frequency. But in the outer layers of the star, that frequency is very large compared to the star's local dynamical frequency or Lamb frequency or Brunt-Väisälä frequency. So in the outer part of the star, these will be acoustic waves. And the waves have to tunnel through this evanescent zone, which in this case is due to a helium-burning convective shell. So you can think of the star as a few different square wells in a quantum mechanics problem. And there's these evanescent zones are some finite width boundary, and the wave function decays away in that region, and only some fraction of the wave flux actually tunnels through into acoustic waves that escape. So what I have done is tried to actually calculate all these factors and put this wave energy transport into stellar models. So you have to calculate things like how much of the wave power gets lost to neutrinos. That's actually the dominant source of wave damping, of linear wave damping at least. You have to calculate things like the transmission coefficient, how much of the wave energy actually escapes. So I've tried to do all this. You can do all this basically from linear theory and estimate the fraction of the wave energy that escapes, that tunnels into the surface as acoustic waves. And it's that wave energy, L heat, that can drive an outburst. So I'm going to show you an example of one such model that I made in Mesa. So there's going to be a lot going on here. I'm going to play a movie. What you're going to see here is a Kippenhahn diagram. This is an HR diagram. So I'm going to start the movie. So what we have going on right here, I'll go a little bit further. So right now we're in carbon shell burning. So this is a convective carbon burning shell here. This is a convective helium burning shell. The surface of the star is right here. At this point, the wave energy is starting to become significant. In this particular time frame, I'm calculating the waves are carrying something like 10 to the 4 L sun of power to the surface of the star. The carbon burning luminosity is something like 10 to the 8 L sun. But only a small fraction of that is getting to the surface. So it's enough to make the star change its appearance a little bit, but nothing dramatic at this stage. If we go a little bit further to, okay, waiting for carbon shell burning. Okay, now neon burning ignites. Neon burning, the wave, or the luminosity in the core can be more like 10 to the 10 L sun. And now in this model, I'm calculating something like, well, it briefly goes up to 10 to the 8, but typically it's more like 10 to the 7 or 10 to the 6 L sun of wave power is getting out to the surface. And that energy dissipates still at large optical depths, but near the surface. And in this case, it's so much power, there's more energy deposited in the outer layers than the binding energy of those outer layers of the star. So this will blow off the outer layers of the star in a super Eddington wind. And that's what you're seeing in this bottom plot. This is the plot of velocity as a function of radius. So the inner part of the star is in hydrostatic equilibrium, but we have this wind launched right at this radius here where the waves are depositing most of their energy. So we have this wind that's blowing off the surface of the star, and that makes the star much brighter. You get this outburst in the HR diagram. And this continues for a while, so I won't go through the whole movie. But you can definitely have some substantial effects. So in this particular model, this is the nuclear burning luminosity in the core. The blue line is the wave heat transported to the surface in this model. It can be of order 10 to the 6, 10 to the 7 L sun. And the red line is the observed luminosity of this model. And so it would be static without the waves, but then when these outbursts occur, the star can brighten by factors of several. Yeah. So you can basically just calculate a wave function. As long as the wave is linear, you can just calculate basically a wave function, how much power gets transmitted. Now, I'm going to come back to nonlinear effects. They're going to change the story, at least in some cases. Certainly in the outer layers it is. What happens is the waves actually go out and they form weak shocks, and that's one of the things that helps them dissipate in the outer layers. But if they become nonlinear in the inner layers, then their energy can just damp out there. So that is an important consideration. Yeah. So most likely the waves go out to the outer parts of the star as acoustic waves. As they propagate into regions of lower density, they steepen. Their amplitude has to become larger. And for acoustic waves, what happens is they start forming shocks. And then the shocks dissipate their energy. So that's what's happening in these models. Yeah, it's not at the surface. It's still below the surface, but it's in the outer layers of the star. And they're weak shocks at first, and that will cause their energy to be thermalized. So we're not actually resolving the waves themselves, but we're calculating where they would form shocks and the rate at which they would deposit energy. So this is an HR diagram of that model. If there were no wave heating, it would just sit right here. It wouldn't do anything. But during these outbursts, the star becomes much brighter and also has much cooler temperature. That's because the photosphere of these models is actually in this unbound wind. So I wouldn't believe this horse diagram. I wouldn't believe all the features here. The main point is that there's probably these stages of outbursts where the star is bright and cool, and stage of quiescence when it's dimmer and hotter. So I'm going to skip that and go to the mass loss rate, which in this particular model is of order 10 to the minus 2 or 10 to the minus 1 solar masses per year, just in like the last year or so of the star's life. But again, this is orders of magnitude larger than you'd expect. And the velocity of this wind are of order the escape speed of the star, maybe a little bit larger. In this model, the waves unbind something like a few hundredths of a solar mass. That doesn't sound like a lot, but this material can go out to radii of 10 to the 14, 10 to the 15 centimeters before the star dies. And then it's sitting there, so when the star explodes a year later, that material gets shocked, and it totally changes what the supernova looks like. You get an interaction-powered supernova. So we're starting to see events. I think a really compelling candidate, there are many in the literature now. A really fun one was this recent discovery by the ZTF group. There's a really nice paper by Anna Ho. This is actually a broadline 1C supernova. So its spectrum looked like a normal broadline 1C, but its light curve was quite different. It has this extremely fast rise that you can't explain by nickel power. It's a much better match with some kind of interacting supernova where the supernova ejecta runs into some circumstellar material, so you get a really fast rise in the optical. And Anna has modeled this and shown that this can be plausibly explained with interaction. And in this case, we actually think we see the outbursts of the star directly. So here's the supernova, but by stacking images, Danny Goldstein was able to detect the progenitor actually a few weeks before the actual explosion. And so we see some points where it looks like the star is an outburst. At other times, there's upper limits indicating that the star was variable. It had these outbursts right before supernova. And then this is about the right time scale to get the shell at the right distance to match this light curve. So it's some really nice work, and we should be finding more and more of these events as time goes on. Now, I was focusing on stars without thick hydrogen envelopes before. If you have a thick hydrogen envelope, the waves thermalize actually at the base of that hydrogen envelope. So in the MESA simulations, what I'm plotting here is the density of the star as a function of radius. What actually happens, the waves thermalize about here, and some of their energy goes, they launch an acoustic wave that goes through the envelope, it causes it to expand, but they also blow out this hollow bubble inside of the star. Now, this is what happens in 1D. In multiple dimensions, this interface here will be unstable, so you'll get some kind of turbulence, and it's not clear what you'd actually see at the surface of the star. But certainly, the effects will look very different in a hydrogen-rich star. I'll come back to this. And that's what I have a postdoc working on right now. But I want to say that in many stars, there are not outbursts. Especially nearby supernova, you can place pretty tight limits. Chris Kachanik and the Ohio State group has done some nice work constraining outbursts in nearby supernova. And what they find is, in many cases, there's certainly no big outburst. So these are some relevant examples. And I think one of the reasons for that is that nonlinearity can really affect how much wave energy gets out. So the calculations I showed you before was for a model where we didn't take into account the nonlinearity of the gravity waves in the core of the star. But they actually can become quite nonlinear. So a useful diagnostic is the wave number times the wave amplitude. And in this particular model, if this number becomes larger than 1, the waves are significantly nonlinear. And in this model, that is what's happening. So probably the outbursts are only happening in certain stars. And one of the things I'm working on right now is figuring out which stars should do that. So one example is if a star doesn't have a convective helium-burning shell, then there's only a very thin evanescent region separating the gravity waves from the acoustic waves. That should help lead to a bigger outburst. That might happen in lower mass stars. This is an 11 solar mass star. Another possibility is certain stars just have greater burning luminosities or smaller transmission coefficients for some other reason. So I'm doing work with a new grad student at Caltech, Samantha Wu, who is calculating wave energy fluxes for many different massive star models. So we're calculating the energy waves deliver as a function of time. And in most cases, they're a bit smaller than the results I showed before, but there are some stars that appear to have much larger energy fluxes. In this case, it's due to a feature that we're not sure if we believe yet. You can have really big wave luminosities if you actually mix some helium downwards into like a convective carbon burning shell. So we're not sure if we actually believe those models, but there are probably some models that will yield much larger wave luminosities than others, and so we're trying to understand that effect. And like I said, I have a postdoc, Xing-Chi, who's actually modeling these wave-driven outbursts. What does this wind actually look like, especially in red supergiants? Can that wave power actually cause enough turbulence to actually expand or partially eject the envelope of a red supergiant? So these are some of his very preliminary models in 2D of wave heating in a red supergiant. And unlike that hollow cavity that we saw before, now we see there is no hollow cavity. You get convection or Rayleigh-Taylor instabilities that fill that in, but you still get some turbulence, and you still basically transport some of that energy up towards the surface layers of the star. So we're trying to understand how much mass you can actually eject, what the pre-supernova density profile actually is. That will affect things like the light curve. So it's a really rich physical problem. There's a lot of aspects and uncertainties to still study. But one of the things I want to highlight is that the waves might be able to explain many events, many phenomenological aspects of supernovae, but there are many things they probably cannot explain. So for instance, the most luminous type 2N supernovae, it looks like the supernova ejecta is running into multiple solar masses of circumstellar material. It's really hard for wave heating to do that because they just don't have enough energy to unbind that much mass from a star. So the most luminous type 2N supernovae I don't think could be explained by this mechanism. Additionally, the wave energy is only something like 10 to the 47 ergs, whereas core binding energy is more like 10 to the 51 ergs. So I don't think this is going to affect the density profile in the core of the star substantially. So that's nice for modeling supernova themselves. I don't think you have to worry too much about this. They are important for seeding turbulence and instabilities during the explosion itself, but they probably won't modify the density profile. But there are many other things the waves are good candidates to create. So there are many type 2P supernovae that show these flash ionized hydrogen emission lines right at the start of the supernova. That's indicative of some circumstellar material that might be put there by wave-driven outbursts. Type 2L supernovae are still not very well understood. Again, they can potentially be explained if there's some circumstellar material. There's a rare class of type 1b supernova called type 1bNs. Those models of those indicate something like a few hundredths of a solar mass, roughly 10 to the 15 centimeters away from the progenitor, which is very similar to the model I showed you before. So I think wave-driven outbursts are a good candidate to explain some of those events. And another thing I'm excited about now are these F-bots, these very fast, luminous, and blue, typically type 1c supernovae that, again, might be powered by circumstellar interaction, this time with the shell that's closer to the star at the time of collapse. So I think these might be explained by wave-driven outbursts in more massive stars. So there's a lot of fun stuff to cover here. So the last thing I want to cover before I finish is that the waves, gravity waves, may actually have a significant impact on core collapse supernovae themselves. So I did some work with Sarah Gosson. This is a paper that just came out this fall, looking at gravity waves excited by convection inside of the protoneutron star. So couple hundred milliseconds after collapse, you have this zone inside of the protoneutron star that's optically thick to neutrinos. So you have convection there, and that convection excites waves. And we estimate the flux in waves is something like 10 to the 51 ergs per second. This can proceed for of order a second. In these supernovae, the evanescent zone the waves have to see is actually pretty narrow. So a large fraction of this energy can get out and propagate outwards towards the shock as acoustic waves. So we've tried to estimate that, and our estimates are of order 10 to the 51 ergs per second. So this is less than the neutrino heating luminosity, so the supernova is certainly not totally driven by this mechanism. But at least there is probably a significant effect of the waves. We're calculating that the wave pressure on the shock is of order 10% of the thermal pressure. So it's a small but significant contribution if these calculations are correct. It's related to the acoustic mechanism that Adam and other people have worked on. In this case, the wave power, it's really originating from the protoneutron star binding energy, which is a huge reservoir of energy. It's of like a few times 10 to the 53 ergs. So you only have to tap a very small fraction of that energy to explode the supernova. And of course, most of that is coming from neutrinos, but another small contribution is from, we think, from gravity waves, which again are basically taking a small fraction of this neutron star binding energy and transporting it outwards. So I'd love to see how these calculations stack up to more realistic simulations and see if the waves have as much of an impact as we expect. So I will conclude and take questions. Thank you.